Excellent. Well, thank you so much for being here. It's been a fascinating day. I think a really great topic for a workshop, which really sort of resonates with me. And high and low field, it's really hard to put, I have a hard time putting my finger on why I'm attracted in both directions. And I think this image kind of scrolling by, definitely gives you some idea. I think it's easier to understand the high field attraction. These beautiful images are just awesome to look at the human body of a living, in this case, not living, but in general, a living person like this. And we're always just sort of chasing that high resolution, low noise image that we've now heard so much about how to handle the noise. And that's definitely explains some things to me. The low field part, I think it's harder to understand, but I think it's a very different set of reasons, and I'll try to get into those a little bit. But before I start, let me just state disclosures. The most important one by far, I think, is that I have an equity and consulting arrangement with a small company called Neuro42, which is starting to make low field portable MRI scanners. I get research support from Siemens. I have some licensing stuff, and pretty much everything I discuss will be a non-FDA approved device. So getting back to the beautiful dead brain images that I was showing you before, it really, to me, the ex vivo brain sample like this, in this case, a whole brain at 100 micron isotropic, sort of shows you where MRI could go if we could just kind of work out the technical details and manage to get this sensitivity and the encoding up a little bit. We've been working on 7T for some time. It's been kind of a slow journey to get to these images, I must say. Our 7T at MGH was ramped in early 2001. And so we now have a second 7T at Terra, but this magnet is actually still working and it's still pretty heavily used. And by the end of 2001, we were actually getting pretty good images. These are some monkey images, which we were really excited about because it showed the basic scanner was working. And in this case, you can see the stria of Gennari in this, and actually what looks like some detail in layer 1 of the primary visual cortex of the monkey. So we were pretty happy with that. And what's happened since then? What's improved? What's really changed in the last 22 years or so, 21 years? Well, on magnets, I can't say that much has changed. The Supercon magnet is kind of largely the same. It's smaller and it's nicer and easier to take care of, but not much changed there. The cryo coolers of the MR systems have changed quite a bit, like about an order of magnitude. They're able to take out almost 10 times as much heat as they used to before. And that has opened up some magnet differences, like the dry magnets, the magnets without a big liquid helium bath, which of course helps sighting because you don't need that quench tube that takes all those gases away should the magnet quench. That's a several $100,000 little bonus at our institution, at least. I suppose some places could do cheaper. I would say that, what's also improved with magnets is dynamic shimming systems have really come up. And I'm not going to talk about that today. We've been doing a lot of work. Jason Stockman and our group, the Yale group, really sort of pioneered this method. And this could end up changing magnets quite a bit too. I will talk about some of our work with rare earth magnets. Rare earth magnets are not exactly new, but they're not as old as you might think. They were invented in the 70s, basically. And they've, of course, become commodity items now. Although they're continuously improving them, I might say. There's been a really steady improvement in gradient coils, and I'll touch on some of this because this has driven some of ours. But our work has really switched to gradients from a peripheral nerve stimulation point of view, PNS. And that's because all the big gradients that we have now, I would characterize as firmly PNS limited. This was especially true of the 300 millitesla per meter connectome gradient. It's true of the Berkeley head gradient that we heard a little bit about earlier, and I'll show some results of. And it's going to be true, doubly true for our connectome 2.0 gradient, a 500 millitesla per meter gradient. But it's really true for your standard Prisma system as well. So, and then finally, of course, parallelization of RX and TX. And this has undergone just a revolution in the last 20 years. And it's really led us to go from, these, when I started, single channel volume quadrature bird cages like this one, that even as quadrature bird cages, it was a humongous coil. It was quite big diameter. And really the image uniformity was valued more than SNR. And to something like this, which is very tight fitting 128 channel brain array that we built for the Berkeley Brain Initiative system. And this is probably a bigger factor in signal to noise than the field strength changes. And of course, it leads to parallel imaging as well, encoding improvements. So I think it's always fair. People talked about field strength dependencies. The coil is such an important part of this calculation that I think you just can't quite leave it out. And it's always ruins. It's never an apples to apples comparison. The closest thing we can really do is a so-called ultimate SNR, where you ask, what is the maximum achievable SNR that you can achieve with an arbitrary array of conductors outside the object. And in this case, Bastian Gurian and our group did this calculation for an actual head model. It was the first time people have done that calculation for a head model. And you can really see some surprising things. And for now, I'll just point out that it gives us kind of hope that high field is not so bad for coils. That, we see what we look at 3T, that looks very much like what we would see in our 32 channel coil or 64 channel head coil or even our 128 channel coils. But it kind of evens out when you go to higher field, and that's kind of promising. I'll come back to the lower field part later. But what's another component, I'll call it part B, that's really improved over the years is image encoding and reconstruction. And I don't really need to tell you guys this because we've been hearing about it all day. And in the last talk, this has really changed a lot. And it's a huge part of the equation now. And there's a lot fewer encoding constraints, non-rectilinear sampling, Chi-P taking advantage of how things alias. Callan Setzenpop, who we heard earlier, he's sort of the master in my mind of that. And it's really led to big improvements. There's also a wider definition of what an encoding field is. And this is really thanks to forward model-based recons. I think Jeff Fessler, really made use of these in CT reconstructions. And he sort of, at least to me, brought them to MRI. And I think there'll be a day where we don't do anything else. We'll forget about the Fourier transform. And this has led to, of course, encoding with the reception fields like sense and grappa, or not necessarily formulated as forward models, although sense could be, and also encoding with the B1 plus and parallel transmit. There's also ability to take those dynamic matrix shims that I talked about earlier, and if they can slew, they can be used to do supplemental encoding too. And we're starting to see people do that. And then I think the last talk kind of showed us, in some of the other ones, some of the power of what I call minor prior knowledge. Obviously prior knowledge sort of has a bad taint to it. If you know what the object looks like, why are you imaging? Why bother? But I think minor prior knowledge can be quite acceptable, and very surprising to me how powerful it is. And we see this over and over again, compressed sensing and joint reconstructions across contrast. I mean, 20 years ago, we would take a T1 image, we'd take a T2 image of the same brain, and they're taken 5 minutes apart, and we'd reconstruct them as if we didn't know anything about the one we just took 5 minutes ago. And that's just lunacy, right? That's just craziness. That the information, mutual information there is phenomenal and should be taken advantage of. And we're seeing that now. I think fingerprinting exploits that and many other methods as well. And of course, we've also heard today about exploiting temporal sparsity in low rank models. So these are really amazing. And what's really great about high field is that what I call the part A improvements, the hardware improvements, especially the coils, are very synergistic with the part B improvements, these encoding and reconstruction improvements. And so what we really got was something that was much better than the sum of its parts. And one of the concerns I actually have about low field is whether this synergy will also prove in lower field. We have a lot more trouble doing parallel imaging. It doesn't really make sense to do that 128 channel coil for half Tesla, or certainly not for 100 millitesla. And that's a bit of a problem. We have to kind of see what that means for us. Anyway, at high field, we were on solid grounds with that synergy, and it really improved images. These are fMRI images. This is just one image from a time series of an fMRI time series taken about 10 years apart. Different field strengths, different coils, but obviously different spatial resolutions. But it's pretty easy to see the benefit that all of this is kind of conspired to add up to. And for our 7T work, what really kind of cemented home that we were getting somewhere was when John Palomini of our group did this experiment. And this had sort of been tried before, so and failed, I might say. So it was really good. It really cemented the idea to me that we've made some progress in the acquisition of fMRI. He showed these flashing noise patterns of these. In this case, it's an M that's warped to exactly undo the warping that you're mapping from the retina to the visual cortex does. It's a logarithmic mapping. And so when he projects these M's and you fixate in the center, what you should see is a normal M activated on the primary visual cortex. And here's the activation pattern. There's a primary visual cortex. Of course, you can't see anything because it's just a slice from a 3D image. So you have to look at it painted on the surface of the cortex. And now you can kind of see that blue M sort of folded into the cortex. And even better, you inflate the cortex so you can see it much better. And now we clearly have a sort of resolution test for our fMRI. We can put these things up and we can see how well we're doing. There's biological effects causing blurring. There's some veins and stuff that are blurring things out. There's, of course, the imaging point spread function. There's signal to noise. All of that we can sort of sum up at a glance. And like I said, this effort had sort of failed before. And so now this was 2010. He probably did this probably 2008. John takes a little while to publish things. So it took a good, 7 or 8 years to make this happen on the 7T. Other 7T sort of success stories were in the periaqueductal gray and the brainstem areas. And here's, again, from an echoplanar imaging from the functional time series, 3 millimeters, 1.5 millimeters, you can sort of see the central brain structure. That's the periaqueductal gray right in the middle. This is a single shot 0.75 millimeter isotropic taken with a head gradient and a 32 channel coil. And now you can really see this donut of periaqueductal gray material. And that was the only structure this group was interested in, and they wanted to see the activation in different quadrants of this structure. And you can really appreciate that we made some progress here. It would be just impossible with 2 or 3 millimeter voxels. So how to make it better? And I mentioned the gradients before, and the gradients were completely peripheral nerve stimulation limited. I think even for the Prisma gradient, and certainly for these connectome gradients. And I just felt that we had no understanding of where this phenomenon was coming from. How can we solve this problem if we can't model it? So a very talented student from Heidelberg started working with our group, Matthias David, also Bastian Gurian, and another student, Valerie Klein, and started to try to do a neurodynamic model. And that involved creating an anatomical model that had the nerves. Because of course, the DBDT creates E fields, but it's not just the magnitude of E, it's a relationship with the nerve. And nerve dynamics are notoriously complicated. They're nonlinear, there's a refractory period. You really need a full dynamic model of it, but it's very well understood. So we know how to calculate E fields in the body, we know how to calculate dynamic nerve models. You just need to put these two together, and then we can really understand the sort of where, when, and how much is happening when you are positioning a body in one of these gradient coils. and then really start to try to fix it. So before, Siemens would make a gradient coil and they'd wind it, they'd make it, and then they'd get 25 or 30 people and they'd test the thresholds and they'd say, aha, that's the peripheral nerve thresholds. Well, that's not very helpful for iterating over many designs. So with the Siemens impulse gradient for the Berkeley group, we went through about a dozen different design iterations with Siemens, and we could tell them exactly what the peripheral nerve contribution was of every wire segment if they were interested. So they could tell us, oh, just look at these segments over here and tell us how bad this change is hurting us. And that really led, I think, to a better gradient in this case. This is a nice head gradient. It has a Gmax of 200 millitesla per meter and a pretty fast slew rate. It's actually faster than that. They're using it at 900 Tesla meters seconds. It's now in the scanner in Berkeley. It's also, our models have been validated. They did the experimental thresholds and pretty much agrees with the model. Matthias is writing up this paper. How do you get improvements by changing things? Well, one thing you do is you balance, say, the thresholds in the head versus the shoulder. A chain should have no single weak link, right? It's the weakest link that matters. You should have all the links have the same strength. So in the second design, for instance, both the shoulder threshold got worse, but the forehead threshold went up, and we have this situation of balance, no weak link. They're all equally weak. And we can really look at with a model, unlike what you can do with testing even, we can say, okay, well, what's the next nerve to fire? Okay, if we fix this, what's going to crop up later? And you can just dial it up, of course, in the model. So very informative for gradient design. And Matthias has made a great progress in incorporating this into design. And I think it really helped. Here's the Siemens impulse gradient, and the GE made a very similar strength gradient coil, which is working very well at the Mayo Clinic. And they published their measured peripheral nerve numbers. And they were actually about where our design started from. So I like to think about it as that would be what we would have gotten. But the design allowed us to increase it by like almost a factor of 2. So I think we get a much more usable gradient. This gray area is the accessible region that the power supply can activate. So that's our parameter space, and you can see we're using a larger portion of it. I just want to leave you with this one thought that nerves are complicated. It's not simple. It's not like SAR. SAR is just E squared. It's nothing. It's a scalar. Nerves are complicated. They're non-linear. It's a direction of the E field relative to the nerve matters. The sign of the E field matters. Polarizing the membrane, hyperpolarizing it doesn't really do anything. It's depolarization that's bad. So, a slew up creates say a positive E field, and a slew down creates a negative E field. They operate completely differently on the nerve. So Natalie Ferris here was looking at trying to change the waveform. So now we have a tool where we can start looking at MR waveforms and say, well, how do they affect the nerves? And you could say, well, it's tough because, yeah, it's completely symmetric, but it just changes whether it activates a nerve that's curving up or a nerve that's curving down. So we haven't really made great progress in this, but we think that there's some things that we can exploit. The refractory period of the nerve is the other thing that we think we can exploit. That you can prepare a nerve, if it's fired, it's much harder to fire a second time. So you can actually prepare it into a sort of refractory state. Anyway, I think this has some great possibilities. But I'm going to move on away from high field because we only have a little bit of time and talk about the other thing that really makes me excited about MR. And it's really stuff that looks like this. And I'd like to, I didn't title my talk high performance low field. I'm actually interested in low performance low field. And I love this quote by Chesterton that if a thing is worth doing, it's worth doing poorly. So if those beautiful images are good, then, mediocre images should be pretty good. And this thing is very different from any other things. You notice the gradient coil's on the outside. It's not going to image the whole head. Maybe it won't even image. Maybe it takes a 1D image. Maybe it takes a profile. Maybe it doesn't image at all. It just samples a region and looks for blood pool products. But the parts of this system could be around $3,000. And at $3,000, it's a monitor. You can afford to have it on the patient all day, just looking for a bleed, say. And that's really different from how we use MR today. So it's wrong to think about this as a diagnostic device. If you have a seizure and you want to figure out whether you have a tumor or something else, you go into a 3T scanner, go into a 7T scanner. Don't use something like this. But this could have its use. And so I love this old joke about the glass of water that's half filled, and the optimist says the glass is half full. The pessimist says the glass is half empty. What does the engineer say? And that's, of course, the question. Well, the engineer says the glass is twice as big as it needs to be. And I sort of feel that way for a lot of uses of MR, and that's motivated some of our low field stuff. That, and when you used to Google portable MRI, this picture used to come up, and that's a CT scanner. So that's a real shame that there's no portable MRI. Now, of course, we have the hyperfine system, and it's a beautiful system that seems to work very well. So finally, we're making some progress on that front. But the inspiration is in these portable systems, bringing the system to the patient, and having MR available in places where it wasn't available before, whether that was a low resource country or whether that's your emergency department. And ultrasound is really the model. Ultrasound has done this, and they've done it beautifully. And there's $700,000 ultrasounds, and there's $3,000 ultrasounds. And they don't take the same quality images. The $7,000 one takes better images and does more stuff. But ultrasound people have figured out when to use the expensive one and when to use the cheap one, and to make use of both of them. MR hasn't figured that out. It's never really been confronted with that problem. Well, I want to try to confront it with that problem, so force it to figure it out. Anyway, I should pick up the pace here. We've all heard a lot about resolution, and I've been working over 2 orders of magnitude from 70 millitesla to 7 Tesla. And it's really less in resolution than you might think. And I realize that these are, this sort of linear relationship is just sort of a guesstimate. And I mentioned this is really the way to look at it. And if you notice that it's the behavior of SNR versus field strength and resolution, or field strength and SNR, is dependent on where in the brain you're looking for these ultimate SNR plots. It's linear and in the periphery, and the center, it's more quadratic. Anyway, like I said, ultrasound has sort of solved this problem. And we've started to use these wonderful Hallbach array of permanent magnets. There's a cylinder, there's a sphere. You can discretize this, and they really have this sort of magical property that the flux return is entirely within the magnets. So there is actually no flux outside the magnet. So talk about a small footprint, it completely contains it. You can put your iPhone, an inch away from this magnet, and it's just fine. And anyway, here's an example of our 40 kilogram magnet. They're super lightweight because we're starting to make them look more like our coils. We want them to follow the shape of the head, or be even more radical. This one's obviously going to have a built-in readout, a built-in gradient as you go down. And this is all work done by Clarissa Cooley, as her PhD thesis started all this in our lab, and Jason Stockman, and a very talented second MIT student, Patrick McDaniel. And now we're joined by Martin Herleman, who is a former employee of Schlumberger, used to work on very similar devices for the bottom of oil wells. It's been a great help. Anyway, here's Clarissa and Charlotte Zappo putting together one of our first Hallbach systems. I won't go into the details. This was a cylinder, as you can see, and it took pretty decent images. This one had a built-in readout gradient, and the other gradients were inside the magnets, just like conventional systems, but it had a built-in readout gradient, and that saves a lot of power and cooling. May or may not be the way to go. We could also rotate it to position that built-in gradient in whatever in-plane direction we wanted. The second one used a more of a dome design. We call it the Hallbach dome or the Hallbach bulb. And it was even tighter fitting and even lighter weight. the magnet alone was about 35 kilograms. And this thing, we put the gradient on the outside. And this is probably one of the only MR scanners that does that. We blast right through the magnet, and it just simply reflects that we're more worried about beefing up the B0 field than we are in gradient efficiency. We actually have more than enough gradient efficiency. It's an unshielded gradient coil. It's small. 10 amps, 20 amps of current is like more than enough to do this imaging. But we could always use more field strength. I'd love to double the field strength of this magnet. We're starting to get some of our first images. I'm sorry to say that because the magnet's so small, the coil is proving problematic, and so we're having some trouble with that. Anyway, Clarissa plans to build one of these for the pediatric ICU. I think that will be a very nice case where it's very difficult to bring the patient to another magnet. We want something we can wheel right up to the bedside. And I just want to end with a little appeal toward these one single-sided magnets. These are in the literature going way back for material properties and other things. This is a planar Halbach configuration that was recently published. But there's also one that's built for prostate imaging. You can see how the patient goes in it here. The patient actually sort of sits on the magnet. And of course, is the natural field gradient that becomes either your readout or your slice select. And the same is true for our head magnet. And here's just some images from this head magnet. And it has a homogeneous region. It's about the size of a hockey puck. And here's just some of our first low field images taken with the system, and also a field plot showing the system. So it's a very different sort of image. It's not going to be a very pretty picture like those 17 dead brain images, but maybe it's something that could still be useful, even if it's, like I said, a 1D or not an image at all, just a free induction decay. So to sum up the challenges of low performance, low field imaging, I'd rephrase Chesterton as to say, it's hard work to make something done poorly be accepted. And that's proven a real thing. And I think the 0.55T systems I'm definitely jealous of, because I think it's going to be a lot easier to do it there. Everybody's first reaction is always the images are not of the quality I'm used to. And, you know, the retort that I would give is like, well, we're going to use it in cases where you wouldn't have any images to look at anyway. So they're better than that. But that doesn't always fly. So it's mandatory that you have to find a niche for the low performance, low field system, which doesn't compete with the higher field systems or even the 0.55T system. You need it to be a unique niche. And anytime you start talking about niche or monitor role, it needs to be inexpensive as well. And so I'll just leave with the final thought of what's driving the cost of MRI. I've looked at this, it's really hard to figure out, I must say. The magnets, well, for our rare earth magnets, we only spend a few $1,000s on the materials. The gradients, it's a couple hundred meters of wires and some 3D printing, and the drivers are about $200 each. It just doesn't add up to much. The console, I'll show you a $500 FPGA with ARM processors is actually probably better than many commercial systems out there. I think one of the problems is really software development costs and general development costs that creep in. Everybody likes to add up the hardware costs, myself included, but the software development costs are substantial for an MR scanner. And for that, I'd just like to end by giving a little plug to support these open source imaging initiatives, because I think that's the only way that will really drive down costs. And I'll just plug two of ours, Jason's gradient driver boards and this little FPGA red Battaglia that's the heart of the Okra, and now a variant of that, the Flocra system that is capable of producing pretty good looking images, spirals, EPI, you name it, all done on a $400 console. And with that, I thank you for your attention. I'm happy to take some questions if we still have time.